Hoaxes use weaknesses in human behavior to ensure they are replicated and distributed. In other words, hoaxes prey on the human operating system. I absolutely love starting with this quote from Stuart Kirkpatrick, because while before we can even begin to talk about computer networks or the internet or all that complex global wiring, we really have to recognize the ultimate network, right? The human operating system. Our innate desire to connect, to share, to communicate, that's the whole reason the digital networks we rely on today were built in the first place.
So, welcome to today's Explainer. We're going to completely demystify computer networks. We're taking a really fascinating journey that scales all the way from just a single isolated computer motherboard sitting on a desk, right up to the sprawling, invisible architecture of the global internet. If you've ever paused and wondered how a quick tap on your screen literally reaches a server halfway across the planet in milliseconds, well, you are definitely in the right place.
Okay, let's take a quick look at the roadmap. We're going to hit 5 main stops today: the birth of networking, scaling up from LANs to WANs, the hardware that connects us, the actual shapes of networks, and finally, who controls the network. Simple enough, right? Let's dive in.
Section 1. The birth of networking. Goodbye, SneakerNet.
Now, in the early days, before the timeline you were looking at even began, we relied on something called the SneakerNet. And yes, it was exactly what it sounds like. Sharing files meant literally putting on your sneakers, copying your data to a physical floppy disk, and walking it down the hall to your coworker's desk. It was, honestly, a total nightmare. Think multiple conflicting file versions, lost data, just absolute inefficiency. But the solution to that nightmare arrived surprisingly fast, largely driven by the US Department of Defense. Just look at this rapid evolution. In 1969, ARPANET successfully connected just 2 nodes, UCLA and the Stanford Research Institute. 2 years later, in '71, boom, the very first email is sent. By 1983, they introduced TCP/IP, which was absolutely crucial because it allowed totally different networks to finally speak the same language. And then, 1990, Tim Berners-Lee gives birth to the World Wide Web. So in just a couple of decades, we went from literally walking floppy disks down a hallway to laying the permanent foundation for a globally connected society. Crazy, right?
Moving on to Section 2, scaling up, from LANs to WANs.
So as those early experimental connections proved successful, the physical footprint of these networks started expanding, fast. And what's truly mind-boggling here is the sheer exponential scale of how we categorize them. Let's look at the top row. A connection covering just 1/10 of a meter, like between a couple devices right there on your desk, is a personal area network, or a PAN. But scale that up to, say, a 10-meter room. Now you've got a local area network, your classic LAN. Keep zooming out, though. Expand to 100,000 meters to cover an entire country, and you've built a wide area network, a WAN, and the big one. If you string those WANs together across 10 million meters, literally wrapping around the entire planet, well, that's the internet. It's the exact same fundamental concept, just scaled up to an exponential degree.
All right, Section 3, the hardware that connects.
So what are the actual physical boxes and circuit boards pushing your emails and streaming videos across all those massive distances? To understand that, we actually have to zoom way back into the microscopic level. What we're looking at here is a network interface card, or a NIC. Every single host device, I'm talking your laptop, your phone, a massive server, they all need one of these printed circuit boards to physically connect to the network media. And burned right into this card is a totally unique code called a MAC address. The easiest way to think about a MAC address is like a permanent digital license plate for your device. It controls its access to the network. Without a NIC, your computer is basically just an isolated island.
Now, once your data actually leaves the NIC, it's going to hit some network devices. On the left here, we have relatively dumb hardware, like a repeater or a basic hub. A repeater's only job in life is to catch a fading electrical signal, regenerate it, and push it further down the cable. That's it. It has no idea what the data actually is. It just amplifies the electrical pulse. But on the right, that's the highly intelligent router. A router doesn't just blindly push signals. It makes really complex decisions. It can read different data formats, it concentrates multiple connections, and most importantly, it connects entirely different local networks across wide geographic areas. It's basically the traffic cop of the internet.
Section 4. The shapes of networks.
So, how do we physically wire all this hardware together? Well, it turns out the cables actually have to take on a specific physical geometric shape. This is called network topology. You've got a bus topology, where everything taps into one long backbone line. You've got a ring topology, where data travels endlessly in a circle. There are stars, extended stars, hierarchies, and the incredibly complex mesh. And the thing to remember is that each of these shapes wasn't just drawn up at random. They were designed to solve very specific engineering problems around space, cost, and reliability. Let's focus on one of the most common shapes out there, the star topology. Take a close look. Notice how the individual nodes, the computers themselves, they don't actually connect to each other at all. Instead, they all run independent, separate cables back to one singular central point. That central point is usually a hub or a switch.
Now, the star topology is incredibly popular, mostly because it's just so easy to install. It's also remarkably robust in one very specific way. Say one computer's cable gets cut. Well, only that specific computer drops offline. The rest of the network just keeps humming along perfectly. But there is a massive disadvantage. Because the nodes aren't directly linked to each other, everything relies entirely on that one central controller. If that central hub loses power, or if it breaks, the entire network dies instantly. It's a textbook single point of failure. Okay, now pivot your mind to the exact opposite philosophy, the mesh topology. In a full mesh setup, every single computer connects directly to every other computer on the network. There is no central hub, none. You might see a highly specialized setup like this in, say, the networked control systems of a nuclear power plant, where absolute protection from service interruption is simply non-negotiable.
But the trade-off here is extreme. With the mesh, yes, you get unmatched point-to-point security, total privacy, and a network that is practically impossible to take down. If a cable breaks, the data just instantly routes around it on a different dedicated link. But the disadvantages? Oh man, the sheer bulk of the wiring required is astronomical. In some large buildings, you literally wouldn't have enough physical space inside the walls or ceilings to fit all the cables. Add in the prohibitively expensive hardware you'd need to actually plug all those cables into, and you quickly see why we do not use full meshes for your average office network.
Real quick, before we leave topology entirely, we have to step away from physical wires for a second and look at logical topologies, the invisible rules of the road. Think of a broadcast topology kind of like a crowded room, where anyone can shout whenever they want to. It's first come, first serve, which, as you can imagine, gets pretty chaotic. Token passing, on the other hand, is highly polite. It uses an electronic token that gets passed sequentially from computer to computer. And here's the rule. You can only speak, meaning you can only transmit data, when you are the one holding the token. It's highly organized, sequential turn-taking.
Which brings us to our final stop, Section 5, Who Controls the Network?
So how do all these computers actually relate to one another in terms of power and hierarchy? Well, it really boils down to two fundamentally different control architectures. You have the egalitarian peer-to-peer setup, and you have the centralized client/server model. This right here is the ultimate showdown of network management.
Let's look at peer-to-peer first. In this kind of network, computers act as absolute equals. Users control their own resources. So if my computer has a printer plugged into it, I can just choose to share it with you, and maybe you share a scanner with me. It is wonderfully cheap, it requires exactly zero specialized administration software, and it's incredibly easy to set up. But it really only works efficiently if you have, say, 10 or fewer computers. Once a business hits that limit and tries to grow beyond it, trying to coordinate everyone's personal permissions becomes an absolute, unmanageable mess.
And that, my friends, is exactly why we introduced the client/server arrangement. This is the go-to solution for large-scale operations. In this model, you have a highly powerful, dedicated central computer. That's your server. The server doesn't belong to any specific user. Its entire job is just to sit there and respond to requests for files, applications, and print services from the everyday desktop machines, which we call the clients.
So once again, a crucial point here is the trade-off. With a client-server network, you gain massive centralized security. You can back up an entire company's data in one single location, and you can strictly control exactly who sees what. But the cost is steep. You have to buy expensive, specialized server software, you have to hire expert IT staff to manage the whole thing, and, just like we saw with the star topology, you introduce a single point of failure. If that main central server crashes, the whole company essentially stops working.
But what if you aren't actually in the office? What if you're working from a coffee shop halfway across the country? Well, this is where a virtual private network, or VPN, comes into play. A VPN allows a remote telecommuter to create a secure, encrypted tunnel straight through the chaotic public internet, plunging right into the protected heart of their company's private client/server network. It securely connects the micro of your laptop to the macro of your corporate headquarters.
We have covered some incredible ground in this explainer today, from the desperate floppy disk days of the sneakernet to the massive global reach of the internet, the invisible logical rules, and the physical shapes that hold our data. But I want to leave you with a provocative thought as we wrap this up. Look at the device you are using right now. If your everyday life, your finances, and your private communications rely entirely on these physical cables, intelligent routers, and centralized servers holding your data, just how secure is your personal node right now? It's a vast, connected world out there. Make sure you truly understand the network you're plugged into. Keep learning, stay curious, and I'll catch you next time.